Okay, in this video, I just want to summarize some of the Laplace transforms that we have evaluated so far, some of the common Laplace transforms that are going to come up frequently in our work in Chapter 6, and then also discuss some properties of Laplace transforms that will be useful when we're solving differential equations. So we've taken the Laplace transform of a constant, and what we've seen is that regardless of what the constant is, when I take the Laplace transform, I'm going to get the constant times 1 over s. So if we took the constant 1, the Laplace transform of 1 is 1 over s, as long as s is bigger than 0. For exponentials, we've calculated these Laplace transforms, and we've got a 1 over s minus a, as long as s is bigger than a. And for power functions, where the power is a positive integer, we did the example when n was equal to 1, but for higher powers, it would follow pretty similarly. You just need to do more iterations of integration by parts, but you could derive the formula that the Laplace transform of t to the n is going to equal n factorial divided by s to the n plus 1 power. And then the trig functions, sine and cosine, look similar, but we want to be sure that we keep the difference between these two on our minds. So I didn't do either one of these in one of the previous videos. I think it would be good practice for you to try and do it. And when you do it, you're going to need to use integration by parts and what's called the Boomerang method to work with these improper integrals for the sine and the cosine. But when you do the Laplace transform of the sine of b of t, then what you get is s squared plus b squared in the bottom, and on top you get the constant b. So one thing that's important to note here is that when we're doing the sine, the top is a constant. And when we're doing the cosine, we still have the same denominator, s squared plus b squared, but now on top we have the variable, which is not constant, s is on top. So they look pretty similar, but that's a really big difference. So these are some of the common Laplace transforms that we've seen. And then on the next slide, I'm going to just summarize a couple of common properties that we can use, and then we'll take a look at an example of how we can combine some of these common Laplace transforms with some of the properties. Okay, so in this video, I want to summarize a couple of key properties of the Laplace transform, and we'll verify the last one since that one is maybe the most complicated of them. So basically, properties 1 and 2 are saying that the Laplace transform is a linear operator. So if I want to take the Laplace transform to a sum of two functions, well, then I can take the Laplace transform of each of them separately and then add the two results together. And that's a pretty quick thing to convince yourself that this is true, starting from the definition, because we can break up sums inside of an integral. So that's how you could verify that. The second property is the second condition for an operator to be linear, which is we can pull out multiplication by a constant. So I want to calculate the Laplace transform of a constant times f. Then all I need to do is calculate the Laplace transform of f and then multiply by that constant. And again, this property is going to follow from the definition of the Laplace transform, which is that it's an integral, and the fact that we can pull out constants from integrals. And this third property maybe is a little bit surprising, so we can walk through this one to prove this third property. But what this property says is that if I want to take the Laplace transform of an exponential times some arbitrary function f, then the result is going to be a shift of the Laplace transform. Okay, so let's prove this third property. So let's start with the definition. So if it's not clear here, it was stated up top that we are assuming that we know the Laplace transform of lowercase f is capital F of s, and this is defined as long as s is bigger than some value alpha. So that's what's given to us. And now we want to go ahead and see what happens when we calculate the Laplace transform of e to the at times this function f of t. Okay, and so using the definition of the Laplace transform, we've got this improper integral from 0 to infinity of e to the minus st times our function. And now the function we're taking, the Laplace transform, is e to the at times f of t dt. And so combining the exponentials inside is going to give us, let's say, we could write this as e to the minus s minus a t times f of t dt, just doing some algebra combining our exponential terms. And so now this is starting to look like the definition of the Laplace transform of f. We just have the wrong power over here. So I'm going to do a substitution here. Let's let w, say, equal s minus a. Well, then what would happen to this integral is we would integrate. It doesn't affect our limits of the integral because those are with respect to the variable t. So inside I would just get e to the minus w t f of t dt, and this is exactly the Laplace transform of our function lowercase f. The only difference is now this is a function of this variable w that we've defined up here. And we would like to write this as a function of s. So this would give us then, replacing w with how we defined it, as s minus a. And so this is going to be defined as long as w is bigger than alpha, and since w is defined as s minus a, then we see that our domain over here is going to be for all values of s greater than alpha plus a. So we're going to add whatever the power of the exponent a is to the domain of the Laplace transform of lowercase f. So that is, there we've proved the third property. So we've got these three properties. In the next video, I want to take a look at how we can apply these three properties to calculate Laplace transforms of functions.